Dear students, welcome to the third lecture on homology theory. So here we start with free abelian group. Free abelian group. So let sigma alpha, where alpha be an index set, lambda be a set, and this sigma alpha can be any object. So here in our syllabus this sigma alpha can be maps or simplices, but in general it can be any object. Now a free abelian group generated by this sigma alpha. So I should mention that this is a set of different object. Okay. So the abelian group generated by this set is a group whose elements are finite sum, this one, say I equal to 1 to some finite number m, where ni sigma alpha I, where this ni, that is the coefficient of sigma alpha I, belongs to Z. Okay, and the indices alpha I belongs to the set lambda. Fine. Now this group is also denoted by span of this set. Okay, fine. So this is called the free abelian group generated by these objects. Now in this case, the set this sigma alpha is called a basis of the group. Okay. Now here we have some observations. Suppose you have a group G which is spanned by three objects, say A, B, C. Okay. Now you can also write it is as same as span of say A, B, and then A plus B plus C. Okay, both are same, because if you take any element from this side, you can generate the element of this by these three element, and this is also the other way. That's mean if you take an element from this span, then you can write it is as a combination of A, B and C. Therefore if G is a span of some object A, B, C, then this is also a span of A, B and A plus B plus C. Now by the definition of free abelian group, you can see that this group is actually direct sum object. That's mean we can write, note that span of the group, so span of sigma alpha, where alpha belongs to the index set lambda, is same as, or you can say isomorphic to the group alpha belongs to lambda Z alpha, where Z alpha is same as Z. Okay, that's mean this group is actually isomorphic to the direct sum of Z's. Okay, so here we have capital lambda number of Z. Now, when we have different group, that is the direct sum and direct product are different. Now, if lambda is, that is the capital lambda, the index set is finite, then this direct sum will be same as direct product, right? We know that. So, if lambda is finite, that is if the index set is finite, then we know that this direct sum of Z is isomorphic to the product of Z. Okay, so when this will be different, so we know that if lambda is infinite, then this direct sum and the direct product will be the different one. So if lambda is infinite, then these two groups are different. In fact, in that case, the direct sum of Z alpha is a proper subgroup of the product of Z alpha, where each Z alpha is actually Z. Why? Because we know that any element of the direct sum can be written as finite sum of the generator, right? But there is no such restriction for the direct product. That's mean if you take your index set lambda equal to the natural number n, then if you take 1 1 1 1, this one, that is eventually one sequence, belongs to the product of product of Z. Okay, but this element is not belongs to the direct sum of Z. Okay, so this is the difference. So now in terms of our n maps, so we shall define some pre-Abelian groups. So now let X be a topological space and say that script X gives a delta complex structure on X. Okay. Now let this set say sigma n alpha, where alpha belongs to the index set lambda, is a subset of this delta complex structure. That is, this is a collection of maps from some simplices delta n to the topological space X. Okay, and let now this delta n X be the free Abelian group spanned by this set, that is sigma n alpha, where alpha belongs to lambda. Okay, that is any element, say sigma belongs to that delta nx, can be written as finite sum. Say summation alpha belongs to say some lambda 1 in alpha sigma in alpha, where this in alpha belongs to z, that is integer, and this lambda 1 is a subset of lambda, is a finite set. So here you should remember that whenever we take some element from the delta nx, it should be a finite sum. Okay. So because I have already seen that many students do this mistake, they generally take the infinite sum as well. But you have to remember that you should take the finite sum, because that is the definition of free abelian group. Okay. Now in other words, if you know the images, say we can write E in alpha, which is the image of the delta n. So if we know the images which is subset of x, right, then we sometimes define that delta nx as a span of this simplices, that is this image of simplices. Okay, because this is just a notation, right? So delta nx can be written as a span of maps, or it can be written as span of the image of the simplices, right? So this is just a notation. You can check that both are isomorphic. And also you have to note that some authors write this is as a open simplices, that's mean write it is as sigma n alpha delta n naught. So some authors write that one, but since these are notations, you can also write, so you can also write this is as sigma n alpha delta n. So both are correct. So here in this lecture we will, or you can say in this syllabus, we will maintain this one. Okay, fine. Now if you know this delta nx, delta n minus 1x and all of this, then you can define a boundary map. Now we define a boundary map, say delta n from del nx to del n minus 1x. So what is my del nx? So this is spanned by the simplices, or you can say open simplices, or you can say spanned by the maps, this one, where each of sigma n is a map from delta n to x, right? And what is this one? So this is a span of say sigma n minus 1 alpha. Okay, or you can say here, right, it is alpha, where alpha belongs to some different index set, say this dash. Okay, so that's mean if we have a delta complex structure, we can define all of this delta n, right, and then we can define a boundary map. And here note that this delta nx can be 0 group as well. So if you do not have such maps, then this group can be 0 as well. For an example, when we have torus or a Klein bottle, so there is, in those cases or in those topological spaces, there is no map from delta 3 to x, right? Therefore, in those cases, delta 3x, delta 4x, all of these are 0, and we start from only delta 2x. Or we can write that in case of if x equal to rp2 torus or Klein bottle, we can see that delta nx equal to 0 for n bigger equal to 3. Fine. Okay, so this is just an example. Okay, in any case, so we define delta n, which is delta nx to delta n minus 1x by the formula. So delta n sigma will be summation of 0 less than equal to I less than equal to n and minus 1 whole to the power I, and if we take again sigma and we restrict over the all the faces, so v0 vi cap, that's mean vi vertex is missing, and vn, or in other words you can write it is as well in this way. So v0 vi minus 1 vi plus 1 vn. Okay, but here in this course we will prefer this symbol. Okay, so that's mean, in other words, so if sigma equal to some, say, alpha belongs to some index set, say n alpha sigma alpha n, then delta n sigma will be summation of, then alpha belongs to lambda, and then take the sum. I less than equal to n minus 1 whole to the power I sigma n alpha restricted over the vertex set v0 vi cap vn. Okay, note that if delta, that is if delta n is a n simplex, say v0 v1 vn, right, then if you take any of its faces, that's mean if you delete any one vertex and then take the span of the remaining vertices, then it will have a delta n minus 1, right, that will be a n minus 1 simplex. Now if we restrict the sigma on this n minus 1 simplex, this is n minus 1 simplex, right, then it will be a map from delta n minus 1 to x. So it will be in my set this one, so delta n minus 1 x, right. So we have a boundary map from delta n x to delta n minus 1 x. Now I state one lemma which is the backbone of the homology theory. So here is the statement. The composition of the map, say delta n minus 1 and delta n, so this composition is identically 0 map. That's mean you have delta nx, you have a map delta n from delta nx to delta n minus 1 x, and then you have another map delta n minus 1 to delta n minus 2x. Okay, now this lemma says if you have a sigma which is in delta nx, then this goes to delta n sigma. Okay, now if you apply delta n minus 1 again, then this should goes to 0. Okay, we shall prove this one. So here is the proof. So first of all, let sigma belongs to del n x, right? Now then define the boundary of del n x. So we know the definition. So this will be summation 0 less than equal to I less than equal to n minus 1 power I sigma restricted over v0 vi cap vn. Okay, now if you apply again delta n minus 1, delta n sigma, then that will be summation 0 less than equal to I less than equal to n minus 1 I, and that will be delta n minus 1 sigma and the restriction. Right? Or first of all we have to understand how to apply this delta n minus 1. Okay, so we write these vertices explicitly. So we write in this way. So v0 up to vi minus 1, then vi is missing, then vi plus 1, and then up to vn. Okay, now you can start here. This is summation 0 less than equal to I less than equal to n. So minus 1 to the power I. So take the third bracket. So now we have to choose another indices, right? Say j. So we have summation j. First we take 0 less than equal to j strictly less than I. Obviously j will be not equal to I, right? Because I is missed here. Now it will be minus 1 to the power obviously j, right? And it will be sigma restricted over say v0 sum vj cap vi minus 1. So it can be up to vi minus 1. So the range of j will be 0 to I minus 1. Then vi cap is vi is already missing. Then vi plus 1 vn, right? So this part plus summation. Now we have already varies j from 0 to I, right? Now it will be I to n. Now say it is I. So obviously j is not equal to I. So j will be strictly bigger than I, so j less than equal to n. So it will be minus 1 to the power. Now we have to define, so what will be the minus 1 to the power. Now we have to remove the points from this side, right? Now suppose j is this one. Okay, now what is the position of this? So here written j equal to, suppose I minus I plus 1, but the position is the ith position. Can you understand this one? Because vi is missing, so there is nothing in the ith position, right? So this is nothing, so this is the ith position. Okay, now if you take j equal to I plus 2, then that will be I plus 1 position. So that's mean here we generally choose minus 1 to the power the position, right? So it will be, the position will be j minus 1. So sigma, so v0 up to vi minus 1, so vi cap, so vi plus 1, then vj, this is missing, vn. Now you have to understand that since there is nothing here, so this is my j minus 1 position. Because of this, so because of this position we assume this. Okay, now we closed my third bracket. Okay, now we combine this I and j. Now note that here we have 0. Okay, we take a different plane. So it is 0 less than I, less than equal to I, less than equal to n, right? And j varies from 0 to I. So by combining these two, one can write 0 less than equal to j strictly less than I, less than equal to n. Okay, and by combining these two summations, so 0 less than equal to I, less than equal to n, and summation I less than j less than equal to n, by combining this one can write a single summation, say 0 less than equal to I strictly less than j less than equal to n, right? So therefore we can write summation, so 0 less than equal to j strictly less than I less than equal to n. Okay, so minus 1 to the power, you can check, it is minus 1 to the power I and minus 1 to the power I and minus 1 to the power j, right? So therefore minus 1 to the power I plus j. So I plus j, and we write sigma restricted over v0 v j cap vi cap vn. Okay, and plus again summation, so 0 less than equal to I strictly less than j less than equal to n, and it will be minus 1 to the power I plus j minus 1. Therefore I plus j minus 1, and we write sigma, the restriction over the vertices v0 vi cap vj cap vn. Now interchanging the indices I and j in the second term, we get, so we can write the first term 0 less than equal to j strictly less than I less than equal to n, so minus 1 to the power I plus j, and sigma restricted over V0, Vj cap, Vi cap, Vn. Okay, and first of all we change, in the second term we change I and j, so it will be j plus I minus 1, so it will be I plus j as well, right? So you can take, it is minus summation minus 1 power, see, j plus I minus 1, right? So we can write here it is I plus j, and we take the minus 1 here. Okay, fine. Since we interchange I and j, so we will get again, so here we interchange I and j, so we get 0 less than equal to j strictly less than I less than equal to n. Okay, and we get sigma, we take V0 up to here we have Vj cap, right? Here we have Vi cap and this Vn. So we get this one by interchanging I and j in the second term, or we can take summation. Okay, now you can check that the first term and second term are same, but their difference is minus, right? So this is equal to just 0. So that's mean delta n minus 1 del n sigma equal to 0 for all delta n x. We can write for all sigma belongs to del n x, right? That is, this map is identically 0. Okay, so we are done. Now since delta n minus 1 del n is identically 0, okay, now you can check that, and this is true for all n. You can check that image of del n plus 1 is a subset of kernel of del n. Why? Because if say sigma belongs to image of del n plus 1, now that implies sigma can be written as sum del n plus 1 tau, right? Now what will be my del n sigma? Now del n sigma will be, so del n plus 1 tau, that will be del n plus 1 tau, but we know this map is already 0, so this is 0. So that implies sigma belongs to kernel of del n. So we can say that since both are group, so image of del plus 1 is a subgroup of kernel of del n. Now also we know that all of these are abelian groups, right? Now since this group, this is a subgroup of kernel of del n, and this is also a subgroup of del n x, right? All of these are abelian group, so we can say that this image of del n plus 1 is a normal subgroup of kernel of del n. Okay, Now since image of del n plus 1 is a normal subgroup of kernel of del n, so we can define the quotient. So that imply the quotient kernel del n, so quotient with image of del n plus 1 is well defined, right? Now this quotient group kernel of del n quotient with image of del n plus 1 is called simplicial homology group of the topological space X, and it is denoted by this symbol. So H n upper delta X. Okay. Now I introduce few names and notations. So we can write here names and notations. So first of all, for each n greater equal to 1, we have defined a boundary map say del n delta n x to delta n minus 1 x, right? That is, it is true for all n bigger equal to 1. Now we define delta 0 as well from delta 0 x to 0, which is just a 0 map. Just a 0 map. Okay. Then we have a long chain. So this way delta n plus 1 to del n plus delta n, or you can write x, right? Okay, so this is my del n plus 1, this is my del n. So here we will have del n plus 2, here we will have del n minus 1. So del will be del 2, this will be del 1, and this will be del 0, which is just 0 map. Okay, and here so del sum mx can be 0. Okay, for an example, so when x is my say RP2 torus or clean bottle, we have seen that delta in x equal to 0 for all n bigger equal to 3. Okay, so it will depends on dimension. So I shall talk later on this one. So anyway, so just remember for a time being this delta n can be 0 as well, but we can even we can write the 0 here. So we have a long sequence. Now this sequence is called this long sequence is called chain complex. Okay, or we can say chain complex of the topological space X. So when we talk about a chain complex of X, you can think of a infinite sequence, this one, where it can be 0 after finite step. Okay, so it stopped at right and it stopped at 0, but it is infinite from the left side. Okay, now this is one name, that chain complex. Now an element sigma belongs to delta nx is called n chain. Okay, that's mean whenever we have sigma equal to summation of, say, alpha belongs to some index set lambda and n alpha sigma alpha n, then that summation, that is that sigma, is called an n chain. Okay, now an element, say again sigma, belongs to kernel of del n, which is subset of or subgroup of del nx. Okay, is called an n cycle. Okay, and an element, say some tau, belongs to the image of del n plus 1, which is again subgroup of kernel of del n, is called an n boundary. N boundary. Okay, and an element of the quotient group, the quotient nth homology group, is called an n homology classes, or in n homology class. Okay, and more specifically, the group Hn delta x is called nth simplicial homology group of the topological space X. Okay, so we know that Hn delta x is a quotient group by kernel of del n, right? So it is a quotient group of kernel of del n quotient with image of del n plus 1, right? So any element, say alpha, belongs to Hn delta x is of the form say sigma plus image of del n plus 1, right, where sigma, which is the element of kernel of del n, is an n cycle. Okay, so these are all about the notation. Now we shall see one example. So we start with my topological space, say torus. Okay, so that's mean this one, so this. So we had this one, right? So this was my U, this was my L, this is A, this is B, and this is C, and all the vertices are V, right? So X, the delta complex structure was given by U, L, A, B, C, V. We know that these are the maps, right? So these are the image of maps. So this is my sigma 1, says it is sigma 2, this is sigma 3, sigma 4, sigma 5, sigma 6. This is 0 dimensional. These 3 are 1 dimensional, and these 2 are 2 dimensional. And our aim is to find the homology group of this topological space. That's mean we need to find the simplicial homology group. So here we can write our aim is to find Hn delta x for n bigger equal to 0. Now here that del 0x, this will be span of sigma 6 0, del 1x, that is span of sigma 3, sigma 4, sigma 5, this one dimensional maps. That's mean these maps which is from one dimensional simplex to the topological space X, and delta 2x, which is span of sigma 1 and sigma 2, and these are the maps from 2 dimensional simplex to X. Fine. And here delta nx is 0 for n bigger equal to 3, because we do not have any maps which is from 3 dimensional simplex to X or any higher dimensional more than 3 dimensional simplex to X. Okay, that's mean delta nx equal to 0. Now we need to find the simplicial homology group. So we need to find the kernel of delta n and image of delta n plus 1 for all n. So first of all we need to find the images of this sigma I. So first of all, say sigma 1 2, this is a map from a 2 dimensional complex or 2 dimensional simplex to U, right? So it is say V0, V1, V2 to U, that is subset of X. Now what will be the boundary of this map? That is what will be the delta 2 sigma 1 2. So it will be my sigma 1 restricted over first we miss the v0, right? So it will be v1 v2, then there will be a minus sign because minus 1 to the power 1, then restricted over v1 will be missed, so v0 v2, then plus, then two vertices will be mixed, then it will be v0 v1, right? So v2 will be missed and it is minus 1 to the power 2, so we have this plus positive sign. Okay, now note that what is my this one. So we know that the boundary of this U, that is the image of U, is just combination of A, B and C, right? Now we can assume that, say take the red pen, say suppose this is my V0, say this is my V1, that is the image of V1, and this is the image of V2. Okay, so for a timing we can assume this. Then what will be my sigma 1 2 restricted over V1 and V2, that is this one, right? So it will be, the image will be B, that means it will be sigma 4. So we will have then sigma 1, that is sigma 4, and this is this one, minus, then the next vertex will be this V0 and V2. Okay, so this will be this one, C, V0 V2. Okay, C, that means we have sigma 5. So it will be sigma 5, we write here 1 because it is one dimensional simplex to C, right? And the next one is V0 V1. Now what is V0 V1? This one, that is A, right? So A means the image of sigma 3, therefore we write here plus sigma 3 1. Okay, so this is the boundary of sigma 1. Now what will be the boundary of sigma 2? Now say delta 2 sigma 2. Now here it is two dimensional, right? Now again we can write it is sigma 2 v1 v2 minus sigma 2 v0 v2 plus sigma 2 v0 v1. Okay, now that is L. Now for a time being we assume that, so in this case, so this is my v0, this is my image of v1, and this is my image of v2. Okay, now if we assume this one, this map, then what will be my this, that is v1 v2. So v1 v2 will be this one, A, right? That's mean again we have sigma 3 1. So we have sigma 3 minus, then we have v0 v2, right? So v0 v2 will be again C. So C means sigma 5. So we have minus sigma 5. Okay, and then we have v0 v1. So v0 v1 means, look at the picture, v0 v1 means it is B. B means sigma 4, right? So we write here plus sigma 4 1. Okay, now you can see that the image of sigma 1 and the image of sigma 2 are same. That's mean you can write that delta 2 sigma 1 2 say minus sigma 2, this is 0. Now that imply this one, that is sigma 1 minus sigma 2 belongs to kernel of delta 2. But we need exact kernel, right? What is the exact kernel of delta 2? Now we know that any element of this kernel will be of the form, say, n1 sigma 1 plus n2 sigma 2, right? Now let this sigma belongs to kernel of delta 2. Now that implies delta 2 of this one, n1 sigma 1 plus n2 sigma 2, that will be 0. But we know that delta 2 of sigma 1 and delta 2 of sigma 2 are same, right? So therefore it will be n1 plus n2 sigma 3 minus sigma 5 minus sigma 4, that is 0. Now that implies, since this is just a object, right, so there is no relation between them, so we have to this one equal to 0. That implies n1 should be equal to minus n2. Now that implies kernel of delta 2 should be spanned by this. So sigma 1 minus sigma 2. Okay, and this is, since it is spanned by a single object, so it is isomorphic to Z. Now what will be my delta 2, sorry, h2 of x? So we know it is kernel of delta 2 quotient with image of delta 3. Now first of all we write what is my chain complex. So we know delta, right, nx, that is 0 for n bigger equal to 3, because that x does not have any image of 3 simplices, right, or more than 2 simplices. So this is 0. So we have 0 to delta 2x to delta 1x to delta 0x to 0. So that is my 0 map. This is my delta 1, this is my delta 2, this is my delta 3. So the image of delta 3 will be 0, right? So this will be only kernel of delta 2. So this will be Z. Okay. Now since delta 3, or we can write delta nx equal to 0 for n bigger equal to 3, that implies hn delta x, that is 0 for all n bigger equal to 3, because there is no such maps, right? Now we got my h3, h4, all of this, and h2. Now what about my h1? So for that we need kernel of delta 1, right? Now say sigma 3, so first we write delta 1x, this is spanned by sigma 3, sigma 4, sigma 5. Okay, where we can write first of all sigma 3 is a map from, say, v0 v1, that is from a 1 simplex to x, so, and image is A, right? Now what is my boundary of sigma 3? Now we know it is sigma 3 v1 minus sigma 3 v0. But we know that if we have any, that is sigma 3, sigma 4 and sigma 5 here, you can check that, right, the boundary will be the same, that is the v only. So in this case this is only v minus v, and that is 0. Okay, and similarly so delta 2 sigma 4 equal to 0, and so this is called delta 1, and delta 1 sigma 5 1 equal to 0. Okay, is it clear why this is 0? Okay, I can explain again. So suppose you have sigma, say now 5 1, so it is suppose from 1 simplex v0 v1 to c, right? Now that imply if you apply delta 1 5 1, so it will be my sigma 5 1 restricted over v1 minus sigma 5 1 restricted over v0, right? But we have only one map starting from 0 simplex to the vertex v, right? This is just sigma 6 0, so we can write it is sigma 6 0 minus sigma 6 0, so this is 0. Or you can write just v minus v. Here we have written that is v minus v, right? So better to write, since it is map, so sigma 6 0 minus sigma 6 0, that is 0. Or you can write v minus v equal to 0. That is also correct, because this map is uniquely determined by the point v. Okay, so that's mean kernel of del 1 is spanned by these three maps only, and which is same as del 1x. So what is my H1? That is first homology of x, that is kernel of del 1 quotient with image of del 2. Now kernel of del 1 is spanned by this sigma 3 1, sigma 4 1, sigma 5 1. And what is my image of delta 2? We have already seen that image of delta 2, right? So this is this. So both are same. So this is quotient by span of sigma 3 minus sigma 5 plus sigma 4. Now note that here we can change the basis. So instead of this one we can write it is span of sigma 3, sigma 4 and sigma 3 plus sigma 4 minus sigma 5. You can check that. Okay, and the quotient with span of sigma 3 1 plus sigma 4 1 minus sigma 5 1. Since one basis element will be is the same, so this is isomorphic to span of sigma 3 sigma 4, that is it is isomorphic to z quotient with direction z. Fine, so we get H1 of x, that is first homology group of x. Now what will be my H0 delta x? Now that will be kernel of del 0, which is just the 0 map quotient with image of del 1. But we know that image of all of these elements are 0, right? So therefore image of this is 0, and kernel of del 1, this is, we know this is del 0 x. So this is actually del 0 x quotient with 0. So this is same as del 0 x, that is it is just the map span of sigma 6. So this is z. Okay, so therefore for torus, x is torus, we get h0 x equal to z, we get h1 x equal to z direction z, we get h2 x equal to z, and for the remaining we get this is 0 for all n bigger equal to 3. Okay. Okay, so this way, if you have a topological space which has a delta complex structure, you can compute the simplicial homology. But in dimension 2, you can compute this homology group directly via this U, L, A, B, C and V. But this will not work in summation in the higher dimension, because you do not know the geometrical, right? You do not know the geometrical orientation. Now since you know the geometric orientation in dimension 2 and in dimension 1, so you can compute this simplicial homology in a simpler way. So in the next lecture, I shall compute the homology group of torus again by using that simplicials, that is U, L, A, B, C, and by not using the maps. But note that this is true only for this up to second dimension. Okay, so whenever we have third dimension, that is whenever you have 3 simplicials or 4 simplicials, then you have to use the maps, otherwise you will get difficulties. Okay, so today we stop, see you in the next lecture.